Introducing combustion. When a chemical reaction occurs, the bonds within molecules of the reactants are broken, and atoms and electrons rearrange to form products. In combustion reactions, rapid oxidation of combustible elements of the fuel results in energy released as combustion products are formed. Combustion is complete when all the carbon present in the fuel is burned to carbon dioxide, all the hydrogen is burned to water, all the sulfur is burned to sulfur dioxide, and all other combustible elements are fully oxidized. When dealing with chemical reactions, it is necessary to remember that mass is conserved, so the mass of the products equals to the mass of the reactants. The total mass of each chemical element must be the same on both sides of the equation, even though the elements exist in different chemical compounds in the reactants and products. However, the number of moles of products may differ from the number of moles of reactants. It is important to note that the numerical coefficients in the equation, which precede the chemical symbols to give equal amounts of each chemical element on both sides of the equations, are called stoichiometric coefficients. So, fuels. A fuel is simply a combustible substance. In this chapter, the emphasis is on hydrocarbon fuels, which contain hydrogen and carbon. Sulfur and other chemical substances also may be present. Hydrocarbon fuels can exist as liquids, gases, and solids. Liquid hydrocarbon fuels are commonly derived from crude oil through distillation and cracking processes. Examples are gasoline, diesel fuel, and kerosene. Gaseous hydrocarbon fuels are obtained from natural gas wells or are produced in certain chemical processes. So in the solid phase, which is coal, its composition varies considerably with the location from which it is mined. For combustion calculations, the composition of coal is usually expressed as the ultimate analysis. The ultimate analysis gives the composition on a mass basis in terms of the relative amounts of chemical elements. Oxygen is required in every combustion reaction. It is important to note that in this model, air is assumed to contain no water vapor. When moist air is involved in combustion, the water vapor present is usually considered in writing the combustion equation. The air-fuel ratio is simply the ratio of the amount of air in a reaction to the amount of fuel. The ratio can be written on a molar mass basis, or moles of air divided by moles of fuel, or on a mass basis, or mass of air divided by mass of fuel. The minimum amount of air that supplies sufficient oxygen for complete combustion of all the carbon, hydrogen, and sulfur present in the fuel is called the theoretical amount of air. The amount of air actually supplied is commonly expressed in terms of the percent of theoretical air. For example, 150% of theoretical air means that the air actually supplied is 1.5 times the theoretical amount of air. The amount of air supplied can be expressed alternatively as a percent excess air or a percent deficiency of air. The equivalence ratio is the ratio of the actual fuel to air ratio to the fuel-air ratio for complete combustion with a theoretical amount of air. The reactants are said to form a lean mixture when the equivalence ratio is less than unity. When the ratio is greater than unity, the reactants are said to form a rich mixture.
In this slide, we will talk about determining the air-fuel ratio for complete combustion of octane. So we are given a problem. We will determine the air-fuel ratio on both a molar and mass basis for the complete combustion of octane with a chemical formula of C8H18 with a theoretical amount of air and 150% of theoretical air, which 50% of it is unexist air. So, as the basis of engineering model, each mole of oxygen is a combustion air is accompanied by 3.6 mole of nitrogen. The nitrogen is inert, which means lack of strength or inability to move, and combustion is complete. Now, since we know that octane with a chemical formula of C8H18 is burned completely with a theoretical amount of air and 150% of theoretical air, that we know that 50% of it is unexist air. So we will determine the air-fuel ratio on a molar and a mass basis. The equivalence ratio is the ratio of the actual fuel air ratio to the fuel. Air ratio for complete combustion with a theoretical amount of air, the reactant are said to form a lean mixture when the equivalent ratio is less than unity. When the ratio is greater than unity, the reactants are said to form a rich mixture. Therefore, in this analysis, for complete combustion of octane with a theoretical amount of air, the product contains carbon dioxide, water, and nitrogen only. And you can see this chemical bond, and we will balance this equation. Therefore, we will apply the conservation mass principle to the carbon, hydrogen, oxygen, nitrogen respectively. It gives us that the carbon, which denoted as B, is equal to 8, hydrogen is equals to 2C is equal to 18, and oxygen 2B plus C is equal to 2A, and D is equal to 3.6A. So solving this equation, we will get that A is equal to 12.5, B is 8, 9 is C, D is 47. Therefore, the balanced chemical equation is C8H18 plus 12.5 times the oxygen plus 3.76 of nitrogen to 8 of carbon dioxide plus 9 of water plus 47 of nitrogen. Now we will determine the air-fuel ratio on a molar and a mass basis. So the air-fuel ratio on a molar basis, we will get the final answer of 59.5 kilo per mole with the air and kilograms per mole of fuel. And the air-fuel ratio expressed on the mass basis, we will get that 15.1 kilogram of air over the kilogram of fuel. So as you can see, it's the same as the As for B, for 100% of vertical air, the chemical equation for complete combustion takes form with this chemical formula. C8H18 plus 1.5 times 12.5 times the oxygen plus 3.76 of nitrogen, and B of carbon dioxide plus D of nitrogen plus E of oxygen. So applying the conservation of mass, we'll get that C is equal to B is equal to 8, H is 2C is equal to 18, O, which is the 2B plus C plus 2E is equal to 1.5 times 12.5 times 2, and D is equal to 1.5 12.5 times 6. We will get those with this. So solving this equation, we will get that B is equal to 8, C is equal to 9, D is equal to 70.5, and E is equal to 6.25. So giving a balanced equation, and we get the balanced chemical equation, so we will arrive this formula. C8H18 plus 18.75 times of oxygen plus the 3.76 of nitrogen, and 8 of carbon dioxide, 9 of water plus 70.5 of nitrogen plus 6.25 of oxygen. So the air-fuel ratio on a molar mass basis, we will get the final answer, which is the 89.25 kilograms per mole in air and kilograms per mole of fuel. So on a mass basis, the air-fuel ratio is based on 22.6 of air, kilogram per air, over the kilogram of fuel, as can be verified. So when complete combustion occurs with excess air, oxygen appears in the products in addition to carbon dioxide, water, and oxygen and nitrogen. Note that balance a chemical reaction equation to complete combustion with theoretical air and with excess air. So we will apply definition of air-fuel ratio on a mass and molar basis.
Example 13.3, burning natural gas with excess air. So the problem is, a natural gas is the following molar analysis: CH4 80.62%, C2H6 5.41%, C3H8 1.37%, C4H10 1.60%, N2 10.50%. The gas is burned with dry air, giving products having a molar analysis on a dry basis: CO2 7.8%, CO 0.2%, CO2 7%, N2 85%. So A, determine the air-fuel ratio on a molar basis. B, assuming ideal gas behavior for fuel mixture. Determine the amount of products in K-mole that would be formed from 1,000 cubic meter of fuel mixture at 300 K and 1 bar. Letter C, determine the percent of theoretical air. Analysis. The solution can be conducted on the basis of an assumed amount of fuel mixture or on the basis of an assumed amount of dry products. So let us illustrate the first procedure. Basing the solution on 1 kmol of fuel mixture, the chemical equation then takes this form. The products consist of B kmol of dry products and C kmol of water vapor, each per kmol of fuel mixture, applying conservation of mass to carbon. Solving gives B is equal to 12.931. Conservation of mass by hydrogen results in, which gives C is equal to 1.93. The unknown coefficient A can be found from either an oxygen balance or a nitrogen balance, applying conservation of mass to oxygen, giving A is equal to 2.892. So the balanced chemical equation is then the air-fuel ratio on a molar basis is, by inspection of the chemical reaction equation, the total amount of product is B plus C is equal to 12.931 plus 1.93 is equal to 14.861 kmol of products per kmol of fuel. So the amount of fuel in kmol present in 100 cubic meter of fuel mixture. At 300 K and 1 bar can be determined from the ideal gas equation of state as NF is equal to PV over RT. So accordingly, the amount of product mixture that would be formed from 100 cubic meter of fuel mixture is 14.861 times 4.01 is equal to 59.59 kmol of product gas. So the balanced chemical equation of the complete combustion of fuel mixture with a theoretical amount of air is, the theoretical air-fuel ratio on molar basis is 9.52 kmol of air over kmol of fuel. The percentage theoretical air is then 1.45 or 145%. Check on both accuracy of the given molar analysis and the calculations conducted to determine the unknown coefficients is obtained by applying conservation of mass to nitrogen. The amount of nitrogen in the reactant is 0.105 plus 3.76 times 2.892 is equal to 10.98 kmol per kmol of fuel. The amount of nitrogen in the products is 0.85 times 12.931 is equal to 10.99 kmol over kmol of fuel. The difference can be attributed to round off.
The study of reacting systems has involved only the conservation of mass principle. A more complete understanding of reacting systems requires application of the first and second laws of thermodynamics. For these applications, energy and entropy balances play important roles respectively. To apply them, it is necessary to take special care in how internal energy, enthalpy, and entropy are evaluated. For this balance, combustion air and products of combustion are modeled as ideal gas mixtures, which its principles play a role. This table summarizes the ideal gas mixture introduced in the previous chapter. So in this table, there are three equations. For mixture internal energy, it is the summation of moles of gas I times specific internal energy of gas I per mole of I. In mixture enthalpy, it is the summation of moles of gas I times the specific enthalpy of gas I per mole of I. Lastly, mixture entropy is the summation of moles of gas I times specific entropy of gas I per mole of I. With the equation of entropy change, specific entropy of I is equals to specific entropy minus gas constant times ln of mole fraction of gas. With the equation and pressure reference is equals to 1 atm, specific entropy is equals to specific entropy I with mixture temperature minus gas constant times ln of mole fraction of gas times pressure divided by pressure reference. Take note that the specific entropy is obtainable from the ideal gas table.
Evaluating enthalpy for reacting systems. In most tables of thermodynamic properties used thus far, values for the specific internal energy, enthalpy, and entropy are given relative to some arbitrary datum state, where the enthalpy and entropy are set to 0. This approach is satisfactory for evaluations involving differences in property values between states of the same composition, for then arbitrary datums cancel. However, when a chemical reaction occurs, reactants disappear and products are formed. So, differences cannot be calculated for all substances involved. For reacting systems, it is necessary to evaluate H, U, and S in such a way that there are no subsequent ambiguities or inconsistencies in evaluating properties. So, an enthalpy datum for the study of reacting systems can be established by assigning arbitrarily a value of 0 to the enthalpy of the stable elements at a state called the standard reference state, and defined by the Tref, or the temperature reference, is equal to 298.15 Kelvin or 25 degrees Celsius, and Pref, which is equal to 1 atm. For example, at the standard state, the stable forms of hydrogen, oxygen, and nitrogen are H2, O2, and N2, and not the monatomic H, O, and N. So no ambiguities or conflicts result with this choice of datum. Enthalpy of formation. Using the datum introduced, enthalpy values can be assigned to compounds for use in the study of reacting systems. Enthalpy of formation is the energy released or absorbed when the compound is formed from its elements. So the compound and elements all being at T reference and P reference, the enthalpy of formation is usually determined by application of procedures from statistical thermodynamics using observed spectroscopic data. So for example, consider the simple reactor in this figure, in which carbon and oxygen each center at Tref and Pref and react completely at steady state to form carbon dioxide at the same temperature and pressure. So the carbon dioxide is formed from carbon and oxygen according to C plus O2, which is equal to carbon dioxide. So the reaction is exothermic, so for the carbon dioxide to exit at the same temperature as the entering elements, there would be a heat transfer from the reactor to its surroundings. So the rate of heat transfer and the enthalpies of the incoming and exiting streams are related by the energy rate balance, which is this equation. So where m dot and h denote respectively mass flow rate and specific enthalpy. So in writing this equation, we have assumed no work and negligible effects of kinetic and potential energy. So for enthalpies on a molar basis, the energy rate balance appears as this equation. Solving for the specific enthalpy of carbon dioxide and noting from this equation that all molar flow rates are equal, we have this equation. It results to this equation. So since carbon and oxygen are stable elements at the standard state, so this equation will become this one. The specific enthalpy of a compound at a state other than the standard state is found by adding the specific enthalpy change between the standard state and the state of interest to the enthalpy of formation. So this is now our equation. Energy balances for reacting systems. So several considerations enter when writing energy balances for systems involving combustion. Some of these apply generally without regard for whether combustion takes place. So for example, it is necessary to consider if significant work and heat transfer takes place and if the respective values are known or unknown. Also, the effects of kinetic and potential energy must be assessed. Other considerations are related directly to the occurrence of combustion. So the state of the combustion products also must be assessed. For instance, the presence of water should be noted, for some of the water present will condense if the products are cooled sufficiently. So for cooling of combustion products at constant pressure, the dew point temperature method of example 13.2 is used to determine the temperature of the onset of condensation.
A fuel cell is an electrochemical device in which fuel and an oxidizer undergo a chemical reaction, providing electrical current to an external circuit and producing products. So a fuel cell consists of two electrodes, the negative electrode or the anode and the positive electrode or the cathode. And between these two electrodes is the electrolyte, which carries electrically charged particles from one to another electrode. And a fuel cell also consists of a catalyst, which speeds up the reaction at the electrodes. So hydrogen is the common fuel for oxidation at the fuel anode, due to its ability to produce electrons without producing harmful emissions from the fuel cell itself. However, hydrogen is not naturally occurring, and it must be produced. So the common methods to produce hydrogen includes electrolysis of water and chemically reforming hydrogen-bearing fuels. So electrolysis of water is the process whereby water is split into hydrogen and oxygen through the application of electrical energy. An example of hydrogen production by reforming of hydrocarbon is the steam reforming of natural gas. To illustrate this, we will consider a steam reforming of methane. So in steam reforming of methane, methane undergoes endothermic reaction with steam to yield synthesis gas, consisting of hydrogen and carbon monoxide. And in the second step, additional hydrogen is produced using exothermic water-gas shift reaction. So hydrocarbon reforming can occur either externally or within the fuel cell. Reaction in a fuel cell is not a combustion process, giving the fuel cell with these advantages. However, despite of these advantages, fuel cells are of limited application, mainly because of its cost. An example of a proton exchange membrane fuel cell is shown in this illustration. So this is a fuel cell that operates with hydrogen as fuel and oxygen as the oxidizer. So a hydrogen-oxygen fuel cell consists of two electrodes, the anode, which is on the left side, and the cathode, which is on the right side. In between these two electrodes is the electrolytes, which allows the protons to pass going to the cathode. When the hydrogen fuel enters the left inlet, it is then oxidized by the anode, which means that each hydrogen atom loses electrons to become a hydrogen ion. Then, the electrons go through an external circuit, creating a flow of electricity. Then the protons at the anode migrates through the electrolyte to the cathode, where they unite with oxygen and the electrons, and this reaction produces water and heat. Another type of a proton exchange membrane fuel cell is a direct methanol fuel cell, where humidified methanol acts as the fuel and oxygen acts as the oxidizer. This type of proton exchange membrane fuel cell relies upon the oxidation of methanol on a catalyst layer to form carbon dioxide. So water is consumed at the anode and is produced at the cathode. Methanol and water are absorbed on a catalyst and lose protons until carbon dioxide is formed. At the anode, methanol is electrochemically oxidized, producing electrons that travels in the external circuit producing power, then going to the cathode where they are consumed together with oxygen in a reduction reaction. So, another type of fuel cell is the solid oxide fuel cell. This schematic shown is an example of a solid oxide fuel cell which operates with hydrogen as the fuel and oxygen as the oxidizer. At the anode, oxidation produces water and electrons. At the cathode, oxygen reacts with electrons to produce oxygen ions that migrate through the electrolyte to the anode. At the anode, water serves as a product, while the electrons passes through the external circuit, creating a flow of electricity. Then it goes to the cathode, reacting with oxygen. The only product of this fuel cell are water, power generated, and waste heat.